thanks, Art and Brian, for those kind words. I guess I'll start the meeting. So I mentioned that tonight is a dual meeting. And what's going on is that it's our regular monthly meeting for Western Colorado Astronomy Club. I'm also a member of BCAS, and I'm also a member of the Mohawk Valley Astronomical Society back in New York, my friends back in New York. And Joel Seif, whose name is up on the screen, is the president there. And Joel, if you want, why don't you put your picture up? So Joel has had internet problems, and his June speaker is even firmer than me about, I don't want to do it unless it's a live presentation. So that got postponed. So what Joel suggested was to take the June meeting for MVAS and lump it into the one for tonight, in particular because our speaker tonight is a member of MVAS. So it seemed like the very nice, cozy, friendly thing to do to join the two club meetings together. So Joel might have a word or two to say before we start the meeting, and then I'll describe our program and turn it on to Gordon. So we have folks from Michigan, and we have folks from back in New York, and our two clubs here in on the Western Slope. So we have a nice crowd of people tonight that we can interact with. So Joel, if you want to say anything before I start the meeting, Joel is the president of MVAS, so you might want to say a word or two. You have to unmute.
Thank you, Nancy, for announcing the Mohawk Valley Astronomical Society, and welcome MVASers. And I just wanted to say, I was going to contact Gordon to see if he could be my fill-in speaker. And as soon as I was about to do that, I received the invitation from Nancy that Gordon was presenting tonight. So I said, okay, that makes my job easy. So thank you, Nancy, and welcome everybody.
Okay.
That's it for me.
Okay, so I'll introduce Gordon and tell you about the program, and then I'll let Gordon decide whether he wants to take questions during the presentation. If people want to unmute, I'll let him decide, but I'll tell you a little bit about our program and our speaker tonight. So the speaker is Gordon Fessinger, and he is, again, a member of the Mohawk Valley Astronomical Society. And his program title is The Development, Operation, and Accomplishments of the Hubble Space Telescope. So the talk provides a short history of the vision and the hard work that led to the approval of the program, an overview of the design characteristics of the observatory. It includes a quick overview of how Hubble is scheduled, pointed, and how the resulting data processed, and a slightly more detailed look at its maintenance and upgrade over the years. The talk concludes with a summary of the program's major accomplishments. So a little bit about Gordon, our speaker. Again, he's a member of MVAS, which is in Central New York State. After a 23-year career as a meteorologist in the US Air Force, he worked another 13 years as a system engineer on the program to field the latest generation of polar orbiting weather satellites. His childhood interest in astronomy was thwarted by the dreaded department store refractor, but he rekindled it in 2017 when he and his wife traveled to Jefferson City, Missouri to view the total eclipse. So I must say that I'm very happy that Gordon came back into the fold of amateur astronomers, and I will allow him to start sharing his screen, his slides, and his sound. And Gordon, once you do that, you can let people know if they can interrupt with, well, I shouldn't say interrupt, I don't like that term. If they can ask questions during your presentation, or if you'd like them to hold it till the end. So Gordon, go ahead and share.
Thank you, Nancy. Again, appreciate the opportunity to do this presentation, something I've always kind of enjoyed. Hubble is something that I have been interested in since it launched. I've had a long time interest in space exploration in general. both manned and unmanned. And Hubble, in my mind, is kind of the perfect blend of both robotic exploration through a remotely operated observatory and manned space program that fixed the thing and has kept it up and running for 30 years. As far as questions go, it's probably a little bit easier if we wait until the end, just because it's hard to see an audience. Obviously now I can't see anything but my screen. I'm one of those people that would also very much prefer to present in person, but that being said, I'll jump into it here. If you do have a question and it just can't wait, go ahead and I'll field it the best I can. So to get started, just a little bit of disclaimers and things. I don't have any personal experience with the Hubble. As you heard during my introduction, I do have some space experience, but that's with weather satellites. The information for this presentation I pulled primarily from the mission websites, the NASA website, the Space Telescope Science Institute website, and the ESA website. And then there were some additional sources that also provided a lot of good information, particularly a couple of books. This Handprints on Hubble that is listed by Catherine Sullivan, she's one of the astronauts that played a significant role in both the development of Hubble over the years. That's a very readable book, and it's quite interesting. Then the second book down there by David Schuyler, also quite in depth, although I didn't particularly care for the way that was structured. And then there's a rabbit hole called the NASA Technical Reports server, and you can go down that rabbit hole and end up in places that you'd never imagine. All kinds of technical reports from NASA are archived on that, and so I pulled some Hubble information from them. Of course, Wikipedia, web searches for some other things, and a couple of articles in astronomy and sky and telescope. Everything, all the images and things are either public domain or I hopefully have attributed properly to the author. So let's get started. And the idea of a space telescope is something that's been around for quite a long time. 1923, Herman Oberth, in his book, The Rocket into Planetary Space, mentioned that, hey, a rocket could launch a telescope into space. This is long before there was even really much in the way of liquid fuel rocketry. In 1946, Lyman Spitzer published a paper that really talked about all the advantages that there would be if you could put a large telescope into orbit. The advantages of angular resolution only being limited by diffraction, not the atmosphere, plus the ability to have better IR and UV observations, again, because the photons aren't passing through the atmosphere. Then in 1962, the National Academy of Sciences recommended that NASA do develop a space telescope. And in 1965, then Spitzer was again named, and he headed up committees to define what the specific scientific objectives of a space telescope would be. Early on, a couple of studies in 1962, they identified a lot of challenges. How are you going to track and point a telescope and track that target from something that's at orbital velocity? How are you going to return all this data? You're going to develop huge amounts of data. How do you get it back? Do you transmit it? Do you return film? Remember, this is early 60s. And there was even question as to whether or not a conventional mirror would last long in the environment of space. But 60s were a time of really rapid development. Both the civilian and military space programs drove an awful lot of rapid development in the aerospace industry and provided solutions for a lot of these things. The early 60s, both industry concepts and the things that NASA was studying, they focused on man-tended designs. So, you take a look at the picture here on the left. What you've got is a notional space telescope that's being launched on a Saturn V. This S2, that's the second stage of a Saturn V. So you've got a rather huge Space Telescope here, and you can see you're docking an Apollo to it. And then, and this idea is that you've got people living in a shirt sleeve environment that are actually tending and working in that observatory. By the end of the 60s, later into the 60s, as technology advanced and we gained experience in space, the idea kind of changed to more of a man maintainable, not man tended. So you see, again, in these drawings here, you've got a suited astronaut who's performing maintenance, and same thing with this artist concept. So you've gone from something that needed a man in a shirt sleeve environment to operate the instruments and maintain the scope, to something that's remotely operated but manned, maintained by astronauts. So in 1968, this ended up being the start of an official program called the Large Space Telescope. And it was going to be launched in 1979. And the plans really emphasized the need, again, for this manned maintenance, on-orbit maintenance, to ensure that there would be a long life for the mission. And you notice that it was quite a large, initially they were talking about a 3-meter mirror on the Large Space Telescope. During the late 60s and into the 70s, there were some precursor observatories that were launched. The Orbiting Solar Observatory, 5 of the 8 launched were successful. And there's a list there of some of the significant scientific achievements that had. But you'll notice that's all X-ray and gamma ray observations that's doing. There was the Orbiting Astronomical Observatory. 2 of 4 of those were successful. But again, now there's not an awful lot of optical going on here. That's all UV and some X-ray. Skylab was a very significant observing mission. They had the Apollo telescope mount. So this area right here, there were 8 instruments on this area that were dedicated primarily to studying the sun. So you can see the list of instruments there. And this was back kind of to the old idea where it was man-tended. It couldn't be operated. Those instruments couldn't be operated from the ground. The crews on board actually operated the instruments and had to go out on EVA here to change out film containers and load more film cassettes. Well, in the 70s, it turned into a fight for funding, even though there was a program that was started in 1968. In 1974, all funding was deleted for the Large Space Telescope. And that led to an outcry by a lot of the astronomers around the country and around the world, and was really championed by Nancy Roman, who was the NASA chief of astronomy. She organized a lot of behind the scenes efforts to raise money and lobby congressmen and get the National Academy of Sciences to publish a report. You see the caption in that picture, the mother of Hubble. She's kind of considered the mother of Hubble for all the hard work that she did, and it led to then Congress in 1978 once again approving funding for the Space Telescope. And to honor her and the work that she did in the time that she was the NASA chief of astronomy, in May 2020, the Wide Field Infrared Survey Telescope was renamed the Nancy Grace Roman Space Telescope. So anyhow, 1978, program's back on track, but there's one problem. They cut the funding in about half. So they've got now $36 million that they can start to use to design and produce this the Space Telescope. Those cutbacks brought some changes to the program. First of all, the mirror size was reduced down to 2.4 meters. Originally, there was supposed to be what was called a Pathfinder space telescope. It was a smaller 1.5 meter space telescope, and it was supposed to prove out some of the technologies and ideas and concepts that would then be implemented on the larger mission. That was cut out, and it brought on board the European Space Agency, with them providing some things and being guaranteed at least 15% of the observing time once the telescope was on orbit. Anybody who's read anything or had any experience with NASA will know that there's a lot of different centers, and the centers, they're like it's like a family fighting for pieces of a pie at Thanksgiving after dinner. You know, they all want their piece of the pie. So the way it shook out in Hubble was that Marshall down in Alabama, they ended up being responsible for the overall development and integration of the hardware, and that they were also going to manage the on-orbit verification of the systems of the telescope. Can it point? Can it transmit data? Does it, are you able to upload, download, etc.? Goddard in Maryland, they were responsible to define the scientific requirements for the scope and for the telescope and the instruments, then manage the actual observing operations of the telescope once it was on orbit. And they were also responsible for doing the verification phase on the instruments to it's called calibration validation, to dial in the instruments and verify that they're working. And as it says there, kind of develop the safe operating procedures. ESA was to supply the faint object camera. They also provided the solar panels and some funding and staff to help. And then the Space Telescope Science Institute in Maryland, they schedule the scope and they deliver the data products. They make the data products available to the principal investigators and other astronomers. So a lot of things that went into the preliminary design of the scope they had to think about. Thermal control was a very big thing. We think about thermal control when we go out on a night, particularly up here in upstate New York, and I imagine the same in Colorado. If it's a late fall or a winter night, you take your scope outside. Well, you got to let it equalize to get rid of some convection currents in the OTA and things so that you can get good observations. In Hubble, they weren't really concerned about that. No air, no convection currents, but they were concerned with how the rapid swings in temperature going from shadow to sunlight twice, once every 45 minutes, the sunrise, sunset in a 90-minute orbit, how that would affect the structure. And this later out, it turns out, and we'll talk about this in a bit, that there were some concerns that they didn't catch. They wanted to, had to figure out what wavelengths to observe, how to do it. Again, how to point and maintain that stability. And here's where the technology over the intervening years really helped in weather satellites and spy satellites. Really, that technology was directly applicable. The launch vehicle was also something that was something they had to consider. The original plans were that it would be able to be launched on multiple launch vehicles. It wouldn't be tied to a single one to allow flexibility. Later, they tied it to the shuttle, and again, that did have some implications down the road. And then a lot of work defining what was meant by maintainability and how did you perform that work. And something that I found interesting, and I had never known until I started reading some of this and researching this, was that originally the thought was that it would only be minor maintenance on orbit. And every few years or so, the shuttle would go up and bring this thing back down to the ground for overhaul. And the more they thought about that, the more they realized that was just going to be a lot of problems. And the shuttle was not turning out to be anywhere near as economical as was originally thought. So that caused a lot of rework and design changes. So it was a 15-year mission life. That's always just kind of a notional thing, you think about it, but that 15-year mission life just meant that everything was designed and it was supposed to return all the science and meet all its objectives within 15 years. And, you know, NASA always over-engineers anything. You take a look at, let me say, Opportunity, you know, Opportunity rover on Mars, 3-month mission life. And 14 years later, it finally died. So the design of the telescope itself was a Ritchie-Chrétien Cassegrain. And we'll go back to our high school conic sections. And so this design has the hyperbolic mirrors, which give a better field of view with fewer optical errors. So you know, if you come over to the conic sections, you just, if you had a plane that bisected those cones perpendicular to them, there's your hyperbola. Whereas, you know, on like my Cassegrain has a parabolic mirror, and that the plane that intersects is at an angle. Incredible pointing accuracy, 7/1000ths of an arc-second pointing accuracy. And then the angular resolution of 4/100ths of an arc-second. That's, you know, pretty good. Although nowadays with adaptive optics, et cetera, large ground-based telescopes are starting to approach that same kind of angular resolution. Only thing of interest really in dimensions is the fact that it gained 3,000 pounds over the years as the maintenance missions. And it was designed primarily as an optical instrument for visible light. It does observe a little bit into ultraviolet as well as a little bit into the infrared. And here was the initial suite of instruments. So we take a look. This is what the thing looks like. You got an aperture door. That's pretty much just the lens cap. Your OTA is in here. And the high gain antennas to transmit the data, receive commands, solar cells to transmit power. Reaction, this area here had a lot of the instruments, the computers, the reaction wheels, things of that nature, the systems. And then the aft shroud in here was held, the instruments for the most part. Closer look at the OTA. This looked familiar to anybody, you know, with a Cassegrain design. Light's coming in, bounces off the primary mirror, up to the secondary mirror, through the baffle into the little aperture in the primary mirror down there, and here's the focal plane. And then the 4 primary instruments along the axial part of the aft shroud there. And then what you don't see, and isn't shown here, there's 3 of these fine guidance sensors, and down below in the 4th slot was the wide field, or is the wide field planetary camera. So the fifth instrument in Hubble. Take a look at the orbit. Had an average height of 340 miles. Here you can see it's inclined at 28.5 degrees. So that's an idea of what the orbital track would be on one orbit. This little GIF here, what that's showing you is if the Earth is this dot in the center and you assume it's not rotating, it just shows the precession of the orbit as the Earth rotates underneath the ground track. So each successive ground track is a little bit further west, and that changes how Hubble can see things in space. What's visible to it, what's not. So actually getting to observe with the Hubble. Some things he had to take into account. This little thing I drew over here, not really to scale, but we've got the sun in the center. Here's the orbit of the Earth. Here's the Earth. Orbit of Hubble around it. So you've got a solar avoidance angle, about 50 degrees. I drew it at 45 degrees, either side of the sun. But roughly anything inside of here, Hubble can observe, won't observe, so that sunlight doesn't intrude into the OTA. For the Earth and the Moon to keep bright light out. And there's another place where you can't take observations, and that's the South Atlantic anomaly. And the South Atlantic anomaly is an area where our magnetic field is the weakest in this area, and that allows the radiation, Van Allen radiation belts, to come closer to the Earth, to the surface. And this causes quite a few problems as satellites orbit through there. So anytime Hubble is going through the South Atlantic anomaly, it's not observing due to all the radiation hits. A lot of words here, but how does it schedule? Anybody can apply for time. No restrictions on the nationality or affiliation. The only thing is that you have to be a U.S. Institution to get funding from our government. Intense competition. About a fifth of the proposals each year are accepted. Every year, roughly, they have a call for proposals, and there's a couple of different types. General observer is the most common. Those are the things like maybe somebody's wanting to observe galactic centers, whatever, things that are long-term, can be viewed at any time, and require a fair bit of observing time. Snapshot observations are things that can be done in 45 minutes or less. And these are used to fill these little gaps in the schedule. Targets of opportunity, they're for transient events, but transient events that can be predicted. In other words, you know, perhaps a comet is making a close approach to the sun, and you want to study what's off-gassing or something of that nature. So that's a transient opportunity but it's known. And then up to 10% of the time is discretionary time for unexpected transients. A supernova, a gamma ray burst is detected, and they want to point to see if they can catch any other light coming from it. So people submit this phase 1 proposal that you're just telling them what you want to observe. Why is it worth observing? What are the targets and where are they? What instruments and how are they configured? And about how much time is it going to take? And then this committee takes a look at them all and makes the cut. Phase 2, again, a lot of words, I won't go into it much, but what phase 2 does is it takes that proposal and actually turns it into computer code, the command lines that would have to go up to Hubble to make the observing program happen. And it's not acceptable until it's gone through a pretty rigorous review process. Then it goes into the scheduling windows. So the Hubble is scheduled on a week-long basis. And you pool this scheduling group, and this is a job I would not want. They're going from a pool of approved programs and building the calendar and building the times and everything where Hubble is actually going to look. And then the loads that were built up here by the investigators are then built into the command loads that actually get uploaded to Hubble to carry these things out. And that happens about 5 days before. That's a lot of work. And I can't imagine, you think about, you got a telescope that's traveling 17,500 miles an hour. Your target sometimes going to be occluded by the Earth, maybe. When can you see it? How long do you see it? It's just an awful lot of things that they have a pretty intense jigsaw puzzle to put together. So here's a little video that goes through how Hubble is actually pointed. So now we've built the schedules, we've uploaded the week's commands, and how does Hubble actually point and hold these targets?
Since its launch in 1990, the NASA ESA Hubble Space Telescope has been exploring the universe. To obtain crystal clear images of distant galaxies and faint nebulae, Hubble relies on sophisticated hardware to keep its gaze locked onto its target. From its vantage point above Earth's atmosphere, Hubble observes the universe 24/7. Whirling around Earth at 28,000 kilometers an hour, Hubble has to rely on its finely tuned pointing control system to make sure its scientific instruments are looking directly at its remote targets. To ensure its gaze never falters, Hubble uses 3 fine guidance sensors located around the circumference of the telescope. These sensors provide precise pointing information for Hubble. They look out for auxiliary guide stars, which enable Hubble to determine its orientation in space and to stay focused on one point. When the telescope drifts by even a minuscule amount, these sensors will detect it. To change its orientation and to correct for drifts, Hubble does not use propellants. Their fumes could contaminate Hubble's observations and limit its lifetime. Instead, reaction wheels steer the telescope, using the elegant principle of Newton's third law. If one of the wheels turns clockwise, Hubble will turn counterclockwise. These 4 massive flywheels spin rapidly under the control of Hubble's computer and move their telescope using the immense torque generated by their spinning. But even at its fastest, Hubble only rotates as quickly as the minute hand of a clock, just 90 degrees in 15 minutes. Detecting such minute movements requires the best and most sensitive gyroscopes in the world. Hubble has 6 of them. They constantly measure if and at what speed the telescope is turning. In combination with the fine guidance sensors, they keep the telescope precisely pointed for long periods, enabling Hubble to produce its spectacular views of the universe. To operate with optimal efficiency, Hubble needs 3 of its 6 gyroscopes. But even if just one was available, its scientific capabilities would not be affected in the slightest. Together, these 3 systems have allowed Hubble to perform its outstanding scientific mission over the last 28 years. And many more new discoveries can be expected in the years to come.
Okay, so Hubble has observed a target. Photons have come in, been recorded. They then get transmitted over to the TDRS, the Tracking and Data Relay Satellite, downlinked into White Sands, the ground station at White Sands. Commercial comms get it to Goddard in Maryland, and from there it's sent over to the Space Telescope Science Institute. They archive it and make it available to the astronomers whose program it was supporting, or eventually to the general public as well. And it gets turned then into final data. As I just mentioned, this group in Baltimore, they archive all of the data, and it's in this Mikulski archive for space telescopes. Everything that you would need to process the data is archived. The science data, the calibration data, the engineering data, all of it's right there. There's a lot of documentation on their website that tells you how and software tools. It's important to note, really, that only some of the data that are captured by Hubble is widely distributed, okay? The general public can go in there once the science, the people whose investigation that data was supporting, once they're through, general public can go in and process that data themselves, much like what you can do from the Juno mission to Jupiter. And there's an awful lot of ways to do that. You know, if you were to search the web for processing Hubble data, you'd find all kinds of tutorials and assistance and where you could process your own images from that Hubble data. So let's get the thing on orbit. First of all, the change to relying on the shuttle forced a slip because of the Challenger disaster. About 3.5 years. It was originally supposed to go up in 86 and it finally launched in 90. And that delay did some good things to the program and had some negative effects as well. One of the things was it allowed a lot of refinement to the plans, the servicing plans, and a lot of rework to make it more maintainable on orbit. It allowed time to complete the ground software and also swap out batteries. One of the things I found, NASA loves the space side of it, and the ground side of it is always behind. It was the same thing on my program, that the ground software to command and control and process the data was behind. Let's get the thing up there, get the data, we'll get it down and we'll work on it later. Negative side of things is that all this time, that 3.5 year delay, Hubble had to be kept in the clean room, had to be powered up, purged, and that cost about $6 million a month. Another interesting thing was that it moved the launch closer to a solar max. At solar maximum, the increased activity on the sun, it makes the Earth's atmosphere expand some, which increases atmospheric drag, even at orbital altitudes that it was. And that drove a lot of detailed trade studies about just how high that Hubble was going to be released. There was a lot of trade-offs because, the scientists wanted it as high as it could get, and the astronauts wanted to make sure that they had margin to be able to get down. And the highest shuttle flights were those to Hubble. So right at the edge of its capability. So in April 90, it got launched and released into space. And when it was released, while that was happening, Bruce McCandless and Catherine Sullivan, they were suited up and waiting to go outside if they had to help unfurl solar arrays, because once the umbilical was disconnected, there was only so much time the batteries would last. And they had a lot of contingencies that fortunately they didn't have to use. They were always disappointed. It's funny, in her book, she says how disappointed she was that she's stuck in the airlock while all her crew is plastered to the window watching the thing be launched or be released into space, and she didn't get to see it. But we've all know this story. Soon as it got first light, it came about that the mirror was flawed, and that was in newspapers and magazines. It was the brunt of late night comics jokes all the time. Everybody had a lot of fun at Hubble's expense because of the flawed mirror. Well, what actually happened? How was the mirror flawed? There was a device that was used to measure the grinding, and that measurement tool was actually improperly assembled, and that led to the spherical aberration. The outside edges, they were ground a little bit too flat, 1/11,000th of an inch too flat. And that caused the spherical aberration. And the biggest effect that had on observations was on faint objects. There was an interesting article, little blurb in, I can't remember if it was Astronomy or Sky and Telescope, where somebody was saying how, the CoStar didn't save Hubble. There was plenty of good data that came down to it without having the aberration fixed. Well, that may be up to debate, but he had a point. Servicing missions. Okay, so back in '79, they had started the servicing missions. They trained on test articles in pressure suits, out of pressure suits, in vacuum chambers, underwater, on the actual hardware sometimes. And that was mainly Story Musgrave, Bruce McCandless, and Catherine Sullivan. And they did a lot of work in developing the tools and feedback. And there was even early virtual reality. Here you see they're doing some work with virtual reality, learning and practicing the maintenance. one beauty about the servicing missions, and one thing that was okay, I mean, yeah, the mirror was flawed, but it was flawed precisely. It was a perfect flaw. And because of that, it could be fixed relatively easily by corrective optics. Interesting story I found, again, the engineer in me loves kind of stories like this. This is actual CoStar here. These are the mirrors that corrected the light and was redirecting it into the instruments on the axial instruments here. And the engineer that came up with this idea, he got this idea for how these mirrors would pop out by a shower in Europe, a shower where the head went up and down and folded in and out. And he looked at that, and it's like the light bulb went off, and he came up with the design for how they were going to get the CoStar mirrors in. So now we get into the servicing missions. The first one, obviously, the big thing to do was to fix that aberration. So they took out the wide field planetary camera and the high-speed photometer. And in its place went CoStar that replaced the high-speed photometer and the wide field planetary camera too. Interesting thing there is that CoStar didn't do anything to help the wide field planetary camera. Luckily, there were two identical cameras. There was a primary that flew and a backup on the ground. And when this aberration was discovered, they were able to rework that backup, and it had its own corrective optics in there. So they replaced, when wide field planetary camera 2 went in, it had its own optics in it. Now, another interesting thing, I talked about the thermal considerations. One thing they didn't get right, the solar arrays, you can see how warped they are here. These are the original arrays. Those arrays would warp like that and cause vibration every time it passed in and out of shadow, and you couldn't observe until the scope stopped shaking. So they had to replace the solar arrays. And then this is an ongoing story, gyroscopes. It seems like the critical items are always going to be those that spin very quickly, the gyroscopes and the reaction wheels, and they're key to the operation, and they are the things that will always seem to break down first. Here's some gratuitous pictures. You see him putting CoStar in. You can see just how big that actually was. Here's the wide field planetary camera 2 going in. And then a look at what it did. Faint object camera, again, the faint objects were what was really affected by the aberration. You can see that here, and then after the fix went in like this. Here's a look at M100 from the wide field planetary camera. And again, this improvement wasn't because of CoStar. That correction was actually done inside the camera. The second mission removed the Goddard high resolution spectrograph and the faint image spectrograph, and they put in a new space telescope imaging spectrograph and the near infrared camera, NICMOS. Fine guidance sensors, again, here you go, reaction wheel assemblies, and then always some miscellaneous maintenance. And I always love to have some pictures of astronauts floating around doing the job. I can't imagine what it's like for these people to be working in an environment like that, on that equipment, in that environment. Unbelievable. The third mission didn't do any equipment swap outs. This was pushed up, and it actually split what was going to be done by the third mission into 2 because 3 of the 6 gyroscopes had failed, leaving only 3 that needed for really fine pointing. And despite what the ESA video said, Hubble can point with 1, but its operation is degraded. Its pointing isn't as accurate accurate, and its tracking isn't as accurate on one gyro as it is with the 3. So anyhow, all of this was to get things up and really get the gyroscopes going. And what I find interesting, they're also going to solid state. When it was first launched, they were recording their data on tape and transmitting it down. And so now they came into the late 20th century and got solid state electronics going. And again, just some shots of them working on the Hubble. The last one, or the second half of that mission, changed out some cameras. Faint object camera came out, a new camera, advanced camera for surveys went in. The flexible arrays, they replaced again. Now they went to a rigid solar array that actually produced a lot more power as well. There you go, reaction wheels, once again, replaced, and then some other things. And this NICMOS, that was an infrared, as I said, the near infrared, and it had internal cooling, which had a lifetime that had expired. So it wasn't cooling anymore. So they came up with a new cryo cooler and a radiator that they could install to extend the life of the NICMOS instrument. Here you see him pulling out the faint object camera. Give again an idea of the size of these things. Here's a look at the NICMOS radiator. So that's helping cool that near infrared sensor. There's the wide field planetary camera here. And a look at the new arrays from those flexible ones that rolled up like a blanket. These ones folded. And then the last mission, they got rid of CoStar and the wide field planetary camera 2 and put in wide field planetary camera 3 and cosmic Oregon spectrograph. They replaced all the gyroscopes, replaced more fine guidance sensors, and they attached a mechanism that will allow a spacecraft to dock with Hubble later to deorbit it when it's finally reached the end of its life. So here's that soft capture mechanism. There's a look at the wide field planetary camera 3. And you can see the improvement over time. Obviously, problem between 1 and 2 was the fact of the sphere collaboration. But between 2 and 3, there's even improved resolution just based on improved optics and things inside the camera and improved sensors. And that's what it looks like now. That was after being released, and that's the last time anybody saw it. What does the future hold? Well, it's expected to last through at least 2026. It's feasible that another servicing mission could go up there and extend the life, but it's really not practicable. I just don't, fiscally, I don't see it happening, and really everything else, I mean, we're talking the scope is 31 years old now, and it's about reaching the end of its life. Again, those gyroscopes are really the limiting factor. Right now, there's 3 of them alive. 3 of them have failed, 3 of them are alive, and one of the ones that's functional is a little spastic. It's a little erratic, and could fail. As a matter of fact, if you heard in the news, I believe it was in March, when Hubble went into safe mode, that safe mode was triggered because commands were uploaded to try to make up for this erratic behavior of that one gyroscope, and then it caused some problems that they didn't catch in ground testing, but has since been corrected. Another point is, a lot of astronomers are really hoping that it stays around so to be able to complement the James Webb Space Telescope. Some people kind of may believe that James Webb is a better Hubble, but it's not a Hubble at all. It really is primarily an infrared observatory, and Hubble can complement those observations from James Webb. So here's some of the highlights of what Hubble has done for science over the years. Age of the universe. Using the Cepheid variables as standard candles, scientists were able to really tighten up the estimate on the age of the universe. It had gone from anywhere between 10 to 20 billion years to about 13.7. And the estimates I read on the error bars for that estimated age, anywhere from 3 to 10%. Some things I read said it improved it to with plus or minus 10. Others said plus or minus 3. And I don't know if that was initially 10 and has since been improved with subsequent observations down to 3 or what. I didn't find anything to tell me what those, why the difference there. It was instrumental in studying the expansion of the universe and the discovery of dark energy. And these supernova search teams, they were using type 1A supernovas and to study the, again, the standard candles, to study the rate of expansion of the universe. And they found beyond a shadow of a doubt that the universe, the rate of expansion is accelerating. And the unknown thing that was causing that, they called dark energy. So there's a couple of examples of what may happen. It appears that dark energy is becoming more powerful, a bigger influence over time. And that would be this curve, which leads to the Big Rip. Current physics under Einstein's model has the universe just kind of slowly expanding, dying out without the Big Rip. And if dark energy were actually getting weaker and gravity more and stronger over time, it leads to the Big Crunch. So there was just down here is a look at some of the distant galaxies where they're actually picking up these type 1A supernovas that they used in that study. 3 of the people in those 2 groups ended up eventually winning Nobel Prize in physics for this discovery. A lot of study of supermassive black holes. The spectra and the images from Hubble well suited for it. So you look at these pictures and what they're talking about here, they were that most of the time when there was colliding galaxies, it led to these, the black holes actually feeding and emitting jets. So, and they were actually able to image the jets. This, I believe, are diffraction spikes in this one, but if you look closely here, you can actually see the jets as here coming from those central black holes. Same thing there. They also were able to confirm the presence of these black holes by measuring radial velocity of stars around the center. So here you can see this is an image of the center of M87, and the stars on this side, over time, they were receding, they were redshifted, so they were receding, and the stars on this side were moving towards the Earth, so they're blue shifted. And the rates, the amount of that shift was indicative of the speed, the orbital speed of these stars. And that speed couldn't be accounted for by the number of stars, the gravitation field of the number of stars that were actually present in the center. So the only thing that, even though it couldn't be seen, the only thing that could be causing those velocities was orbiting around a supermassive black hole. Hubble imaged the deep field and ultra deep fields. Okay, so these images, here was the first one was the deep field, where one of these astronomers said, hey, let's point Hubble at a blank spot in space for as long as we can and see what we see. And they saw thousands of galaxies. Well, the deep field, those galaxies took back to about 1.5 billion years after the formation, after the Big Bang. Then they went to an ultra deep field, even longer. And that got observations back to about 800 million years after the Big Bang. So these galaxies are as they appeared only 800 million years after the Big Bang. Then they went to an infrared, the ultra deep field infrared, and that extended things out to about 480 million years before the or just after the Big Bang. That's as far as Hubble can go, because anything older than that is redshifted beyond what Hubble can see. Its infrared detectors won't pick up the light that's redshifted that far, and that's where the James Webb Telescope is going to come in, and James Webb is going to get us back to about 200 million years after the Big Bang. I was surprised at the amount of planetary science and exoplanet science that Hubble has been involved in. In these cases, a lot of words there, but they're talking about how its observations were supporting and refining the theories of planet formation. And in this case, it was the differences in the color of the disk of protoplanetary material that's surrounding the central star. And the darker disks are flatter and denser, and that means it more easily can form planets, whereas the lighter disks are not as dense, more diffuse. Also, they discovered an awful lot of things going on, like, okay, so here we're looking in the Orion Nebula. And unfortunately, with this picture, it's a little small. If you were to see this picture full screen, each one of these is pointing into an area, a star formation area. And what they found was that the young stars make it very difficult because of the amount of UV radiation blasting out of the young stars. It's making planetary formation very difficult. The disk hard time surviving early. So it takes a little while. Hubble was also the first to take an actual visible light picture of an exoplanet. In this case, the central star, represented by that dot, has actually been blanked out on the light from that star because it's so bright, which allows you then to see the disk of protoplanetary material around the side. And right there is Fomalhaut B. And that was its position here. You see, they show it where it was in 2004, 2006. So you've actually seen movement. It was the first picture, actual visible light picture of an exoplanet. Doing some studies with atmosphere of exoplanets. Discovered methane on a planet, Jupiter-sized planet, and also water vapor. And one of the most important things about this is the fact that the more capable observatories that are planned and upcoming, James Webb being one of them, it's kind of a proof of concept that those new scopes will actually be able to do worthwhile study of the atmospheres around these protoplanets, these exoplanets. And that's all based on spectrographic analysis of the light of the star as it shines through the atmosphere on the limb of the planet. Hubble found 4 moons of around Pluto that were unknown at the time. In this image, this black band is much darker because it's a combination of images where Pluto and Charon are so bright that if you image them, you would never be able to see the other 4. And it was used extensively to study objects in the Kuiper Belt. And they found the second target for New Horizons after it completed the flyby of Pluto. It was ground-based telescopes couldn't find anything for New Horizons to get to after Pluto, but Hubble did. There's some non-scientific accomplishments as well. Most of it is contributions to aerospace engineering, and it's been a marvelous laboratory for studying structures and equipment and things on orbit. Okay, graphite composite in the vacuum. Studying how optics are contaminated by off-gassing of things around it and by human servicing, radiation damage and behavior of things over a long period of time. You know, one of the things they learned about the gyroscopes and was that they were using pressurized oxygen to push this fluid that suspended the gyroscope's wheel, and that was causing the electric wires to corrode. Now, for the life of me, I don't understand why they would have used pressurized oxygen to begin with, because oxygen is so reactive and corrosive. But yeah, hey, geez, then they switched to nitrogen and they lasted a little bit longer. Mirrors have lasted much longer than what they thought. After 30 plus years, 31 years, there hasn't been any measurable degradation in the mirror. And then all the work to develop the procedures and the tools, et cetera, for the servicing missions played a big payoff. This is a foot restraint that goes on the end of the robotic arm. It was on the end of the robotic arm in the shuttle. There's a long story in Catherine Sullivan's book, very interesting, about how Bruce McCandless worked to develop that and what it did for things and how revolutionary it was. And now it's standard. Tools, the torque wrenches and all these things were directly applicable to getting the ISS built and for any later construction in space. There's also been some intangible contributions, in my opinion, really. The biggest thing that Hubble has done is kind of just fire people up and get them interested. When they see beautiful pictures like the Pillars of Creation here, it gets at least some people fired up and interested in science, engineering, astronomy. And that can't be a bad thing. I mean, especially the way science kind of is viewed nowadays, you get people interested in it and thinking about it and understanding what it's really all about. Can't beat it. So that's all I've got. Sorry for all the words and not a lot of pretty pictures, but it's the old engineer in me that did things for critical design reviews and et cetera, where you had to have a lot of words and pictures didn't really matter so much. Does anybody have any questions?
Yeah, I have a,
Oh, go ahead.
sorry. My name is Vic Barton. I'm I'm a member of the Astronomy Club, and you may have already said it, but I missed it. What, here on terrestrial telescopes, when you're taking photos, you usually go with a German equatorial mount. You use, right ascension and declination, and you go on the North Star, and etc. Well, that's orbiting the Earth at 17,500 miles per hour, and it's. What are they? Are they using RA and declination, or what do you use?
I am not 100% sure. That would be, the Space Telescope Science Institute would have that answer for sure. But I believe that it is, right ascension and declination, as it would be for somebody on Earth. But the beauty of it is, that Hubble can go in 3 dimensions, not a problem. So, you don't have to worry about polar alignment and things of that nature. And when you're pointing, but I believe because they do have to obviously use a coordinate system. That's a good question that I'm not positive of the answer on.
Okay, thanks.
Hi, Gordon. This is Nancy.
Yeah.
I'm curious as to why the name Hubble was chosen. I see Mr. Spitzer there was one of the people having the ideas. Why was it named after Hubble?
Well, mainly because, as I understand it, he was kind of the discoverer of the expanding universe, and that those little fuzzy blobs out there were actually galaxies and not nebula. And one of the primary objectives of Hubble was to measure the age and the expansion of the universe.
Logical? Thank you.
Gordon, this is Brian Cashin. When you were talking about the cone of avoidance, the 50-degree cone of avoidance that Hubble could not look at because of the sun, is that more related to the potential for a negative heat impacts from the sun, or actually just light on the sun, or both?
That it would have to be both, because you're inside, you think of the heat. I mean, the inside of that OTA is black, which is gonna, if it's exposed to the sunlight, it's gonna be heating up. So you're stressing the structures with heat, and you're also starting to get very bright light that may saturate and even damage the detectors.
Thanks.
Gordon, can you explain again a little bit about this? I think it was called the South Atlantic Anomaly. That's the first time I've heard of that. I'm curious about it.
So the way the magnetic field, the Earth's magnetic field goes, and I can't explain exactly why this is the case, Nancy, but in this area over South Atlantic and South America is our magnetic field is at its weakest. And that allows then, where the most of the time the radiation, the particles of radiation are being directed around the lines of the magnetic field, and they're further out. Here, it allows a higher dose of radiation closer to the Earth's surface, and it's very. I mean, again, I'll talk to the program I was on. We had to continue to observe because we're weather sat, so we didn't curtail observations there, but once, maybe twice a month, we would trip and go into a safe mode flying through there, just because of the radiation, the increased radiation. And again, it's due to the fact that in that area, the Earth's magnetic field is at its weakest, and therefore shields us the least.
Thank you. That's my definite learn something new every day. That one right there.
And that's something that's very, I mean, the ISS folks think about that quite a bit, because they increase their radiation exposure every orbit when they go through there.
Hey, Gordon, this is Robert Foster. I wrote a little question in here, and I figure this must happen, but I wonder how much of a problem it is. The Hubble's making an orbit every 90 minutes, I think you said. But if it's observing something at any given time, does the Earth get in the way of that path of view? And how often does that happen? And what do you do to mitigate it?
Well, it depends. It depends on obviously where that target is in relation to the Earth. So if we were to look at this and say we're imaging, we're worried about this star here. Okay, so you're going to be able to see that, and we'll forget that the sun is there, so we don't have an solar avoidance angle to worry about. You're going to be able to see this target from the time Hubble gets about here on its orbit until the time it's back around to about here on its orbit. And then there's going to be a certain section where it's obscured by the Earth. But if it's something that's outside of the plane of the orbit, above or below, you
Sure.
might be able to see it almost all the time. And
Right.
that's where, I kind of jokingly said that I can't imagine the work that goes into scheduling the actual observations, how it's pointed, where it's pointed, for how long it's pointed by those folks in Baltimore, because they have to take all that into account. They have to know when that is gonna be visible. And you think about it, okay, so again, we'll say you're interested in this galaxy, but you wanna the deep field. You may not be able to, you may want hours of observations in this galaxy, but you can only get maybe 45 minutes in an orbit. So they have to go to that pool of approved proposals and see what could fit in. When I can't look at that, what can I see that people want to look at? And it's got to be incredible. I just can't imagine, and I can't imagine what happens in that place, like in March, when all of a sudden Hubble goes into safe mode, and you've got a principal investigator who's put years of work into, and his program is running, and all of a sudden Hubble's bleh, crazy, a lot of work.
Hmm.
Well, I guess a follow-up, is Hubble always in the same orbit, or can the orbit be modified to get better viewing angles?
Yeah, no, it's in its orbit. I mean, the orbit it was released in is the orbit that it's in. The shuttle may have been able to change. Well, even then, because the shuttle was up at its top of its limits, it probably couldn't do much of a change of orbit when it had it grappled. But because there's no propellant on board, as I said, everything, all the pointing is done by reaction wheels and differential torque of those reaction wheels. So there's no way to get out of that 23.5 degree orbital plane. It's stuck there for, until the only difference is atmospheric, the drag will eventually bring it down. So height is the only change.
Okay. All right, cool. Thanks very much.
If anybody else has any questions for Gordon, just unmute and ask them.
Say, Gordon, Art Trevina here. I had a question about the docking adapter you mentioned for when the Hubble HST reaches its end of life. Does NASA have a specific satellite in mind for docking with the HST and bringing it down to a controlled, in a controlled way?
No, there's no plans for any kind, well, nothing firm right now for any kind of tug or anything that can, but what they've got a standard now, they've got that standard grapple feature. So they know what they need to do. Now, there's a lot of work going on in this field right now, and Northrop Grumman is doing an awful lot where they're actually going up and grabbing ComSats and geostationary orbit and extending the life. They're actually docking, and these are satellites that aren't made for servicing. They're grabbing onto the old liquid propulsion engines. So, when it comes time, I don't think it would be terribly long. It's not like it would have to be a huge developmental effort, but they put it on there, but there's nothing to bring it down yet.
Thank you.
This is Terry Hancock here from Grand Mesa Observatory. I just wanted to thank you, Gordon, for the great presentation. And, it really was great. And it's really amazing what the Hubble telescope has done for the astronomy community since it was launched. I'm in touch with a lot of guys that do astrophotography, and you mentioned earlier about people grabbing the data and doing their own processing. I've never done any, but I've had students and contacts that have done quite a lot. And, you know, we owe the Hubble telescope for things like introducing the Hubble palette, which is one of my favorite things when it comes to doing astrophotography, photographing in narrowband. I think the Hubble telescope actually introduced that, and it's become very, very popular amongst amateur astrophotographers. So
That's a
yeah.
specific enhancement curves and things.
Hubble palette, which is photographing in narrowband filters. The most popular type that amateurs are using is hydrogen alpha, oxygen and sulfur, and combining those to create a false color image, which is a bit like the Pillars of Creation. I think that was done in Hubble palette, possibly not with using exact same filters, but very similar, I believe. And a lot of my images, probably 80–90% of my images are all done in using double palette technique for the processing. So yeah, it's become very, very popular among amateurs. So all thanks to the Hubble telescope.
Anybody else have any questions for Gordon? Well, I certainly joined Terry in yeah, commending your presentation, the visuals, and I definitely can see the engineer in you there, Gordon, with the detail, but the visuals on the presentation, it's just very, very nicely done and very well presented and lots of great information. Yeah, I've seen a lot of stuff about Hubble, but this is just a very comprehensive and nice presentation. So thank you very much.
I could have shown an awful lot of pictures, but you know, you see the pictures all the time, and I really got drawn into the story of how it got to be what it was and what it takes to keep it up there.
Yeah, so thank you. And I think that unless anybody has any more questions for Gordon, I don't think since we have a joint meeting going on, I don't think we'll delve too much into any specific club business. Joel, I just wanted to ask you if you had any other additional comments as well from your end.
Yeah, Nancy, I would like to really thank Gordon. I thought that was a very superb presentation. Anyone joining in would have thought he must have worked on this thing, because he seems like he really at least understands a lot of the mechanisms and concepts behind it. The one question I have for Gordon is, I don't recall you mentioned the orbital height. Do you know what that is?
Yeah, approximately 340 nautical miles, but obviously that varies, and it'll be lowering as atmospheric as drag over time brings it down.
So what was the reason why they picked that as its orbit?
It was as high as the shuttle could get it and still have a sufficient reserve that the astronauts would agree to fly, because they didn't want to get it. I mean, people wanted to get it as high as they could. And another point is that at a lower orbit, it becomes harder to point. Again, you don't think that drag is that much of a factor, but with the big solar panels and things, just torquing that thing around, it gets harder the lower it gets. So there was a big trade-off, Joel, between getting it as high as they could and making it safe so that if there was a problem on the shuttle, they had enough fuel for emergency deorbit.
The James Webb telescope will be 1 million miles from Earth at a Lagrange point. So there will be no maintenance on the James Webb.
That's kind of scary.
Gordon, this is Douglas Grote. I want to thank you for something. That is the audio quality you have. I've had trouble hearing some of the presentations before, and this audio quality was excellent. I thank you for that.
Okay, does anybody have any other comments or questions about either the program or club business for any of the 3 clubs involved here? Anybody have any questions or comments about general club stuff?
Nancy, this is Joel. I'd just like to thank you for inviting us. And when we get back to live meetings and such, I hope that our connection with your group does not end at that point. So we'll have to, see if we can make some sort of an occasional remote gathering, I think.
I think I agree. And I specifically remember one time before the pandemic, Douglas and I tried to Skype into one of your awesome presentations that was going back east, and we had a really difficult time. So now life is much easier and we can all participate in everybody else's programs and stuff. So I agree that we're not going to let that connection go now that we have it, and let's just keep sharing.
And that's it for me in terms of comments. So thank you very much.
Okay, Art or Brian, do you guys have anything from the BCAS side you want to talk about?
Just wanted to thank Gordon for an excellent presentation. I learned a bunch. It was great. Appreciate it.
Yeah, ditto from me. Thank you, Gordon. And thanks, Nancy, for hosting this all along. It went very, very smoothly.
I think we're getting the hang of the Zoom thing, right? Finally. All right, well then, if nobody else has any comments, then I want to thank everybody for participating and joining in and asking great questions. And we all again thank Gordon very much for his awesome presentation. So thanks everybody, and I'll end the meeting, but thanks to everybody and stay safe.
Thank you all.
Bye, everybody.
Good night.
Good night, everyone.
Thank you. Good night.